Hi, hello, my name is Yuchen. Today I want to introduce our work about defending against microphone-based attacks with personalized noise. This is a joint work with Ziyu, Xiang, Seong, Kapadia, and Williamson, conducted at Indiana University, Bloomington. Microphones are everywhere. There are an estimated 3.3 billion actively used smartphones around the globe today, and there is a growing market for digital assistants such as Google Home and Amazon Echo. These microphone-enabled devices feature an always listening mode to support voice-based commands. As a convenience over physical pressing a button, people can trigger voice commands with spoken phrase such as Hey Alexa, OK Google, and Hey Siri. Microphones in this ubiquitous device, however, raise significant privacy concerns. First, digital assistants conduct speech recognition in the cloud once it has locally recognized the trigger phrase. However, they are often incorrectly triggered through false positives and violate people's privacy by uploading unauthorized conversation to the cloud, or worse, by sending them to contacts by incorrectly interpreting casual conversations as complex commands. Second, even if these microphones are set to off, attackers can potentially record conversations through eavesdropping malware. Microphones in general pose a serious threat to the privacy of users. They are ubiquitous in people's lives, can be easily used, and yet have no clear, tangible way of being disabled by the user. Unlike cameras, which also pose privacy risk but can be covered more tangible by users, like using stickers, microphones are not easily disabled or muted. In the past, external microphones were needed and could be simply disconnected to provide tangible assurance of privacy, but recent devices need to address embedded microphones. Users have viable options to tangibly shut off the microphone to be assured of their privacy. Apparently, one option is to shut down all your devices when you don't want to use them. However, people have legitimate reason to have their smartphones and personal assistant on, such as receiving incoming calls. However, there are situations when one would prefer only the microphone disabled. Therefore, we seek defenses where a user can choose to mask or obfuscate their conversation while retaining the function of their devices. Existing microphone masking techniques mainly use either ultrasonic signals or random loud noise to jam the embedded microphones so that the mixed speech cannot be recognized. However, there are still drawbacks to these methods. For random loud noise, user will be disrupted by the noise, and the existing noise canceling technique can help to directly remove the injecting noise. For ultrasonic signals, user may not be aware or sure of their existence. For ultrasonic jamming, it is also useful to craft a more effective jamming noise. Therefore, in this paper, we seek to confuse eavesdropping adversaries by designing customized pattern of noise tailored to target user or victim. These are played through an external speaker into the microphone with the goal of rendering captured speech and noise mixture unintelligible to both ASR and human adversaries. This diagram shows how attacker can eavesdrop a conversation from a voice-controlled device. First, the human is captured by embedded microphone in the device. Then, the analog to digital converter is used to digitalization and quantization to convert the input voice into a digital speech signal. The attacker can access the digital signal and can accomplish the attack by either directly listening to the signal and manually recognizing content, or can use a state-of-the-art ASR system to convert the signal into text transcript. By injecting defensive noise physically into a microphone, we can obfuscate speech targeted by attacker. When the attacker receives the noisy mixture, they cannot understand the content by listening to it. The ASR system will also be misleading and produce an incorrect transcript. Before we dive into the detail, we first clarify our threat model. First, we assume a remote attacker who must rely on compromised device with a microphone to eavesdrop and target conversation. This is also mean that attacker does not have physical access to the victim's space to place unauthorized microphone or bugs. Second, we assume the attacker can gain full control of the target device or already have full control. For example, a user might consider the manufacturer of the device to be a potential adversary while the user is having a private conversation. Third, if the ASR failed to the attacker has the capability to physically listen to the captured audio. Thus, and the defense must be robust against both ASR and human-based attackers. We used word error rate to evaluate the attacker's performance at correctly recognizing the capture speech. Word error rate is a fraction of the mistakes or errors in the transcription. Errors including incorrect word substitutions, deletions, and insertions by comparing the ASR system's output transcription to the ground truth transcription. Word error rate is computed by dividing the number of errors by the total number of words in the reference transcription. Since the purpose of our work is to obfuscate the speech content, we want the word error rate to be as high as possible. Our baseline defense against eavesdrop is to add a random non-stationary noise to the environment. The reason that we choose non-stationary noise as our baseline is the statistic properties of stationary noise remain unchanged over time as opposite to a non-stationary noise, which varies with time and thus harder to recognize and remove. The SNR level shows the ratio of the power of the speech to the power of the injecting noise. Lower SNR level indicates the noise is louder. Since we want to keep the disturbance level low, so we want the SNR level as high as possible when the word error rate is satisfying. The two baseline non-stationary noise that we choose are random babble noise and cafe noise. Babble noise contains multiple people talking simultaneously, and cafe noise contains sounds like cafeteria environment. Let's hear what's the noise like first. So that's the babble noise. And that's the cafeteria noise. Then let's hear the mixed speech.
The goose was brought straight from the old market.
That's the mixed speech between the target speech and the babble noise.
The goose was brought straight from the old market.
And that's the cafeteria mixture. As you can hear, all the mixture are under a 0 dBSNR level, where both the signal and noise are at the same decibel level. By mixing the target speech with the baseline non-stationary noise, we can find that the contents has been obfuscated. However, we can still hear some words and phrases from the target speech. Finally, let's hear what the clean speech is.
The goose was brought straight from the old market.
One problem that we find from the baseline noise is that we can still recognize some contents from the mixture because the voice characteristic of the background noise is not similar to the target speech. Our approach uses target user's own voice to generate a specific babble noise to mask the actual speech. Here, multiple tracks of convoluted utterances are stacked together to generate this specific my babble noise. First, let's hear what's the target speech we want to mask.
Fine soap saves tender skin.
Next, let's hear the reference signal provided by another speaker used for voice conversion.
Belief without evidence in what is told by one who speaks without knowledge of things without parallel.
Next, let's hear the voice converted signal.
Belief without evidence in what is told by one who speaks without knowledge of things without parallel.
As you can hear, the converted signal has the same content as the reference signal, but in target user's voice. We used multiple of these converted signals to craft the my babble noise. Finally, let's hear the mixer speech. We can find that the content of this mixture speech is harder to recognize than the baseline mixtures. Now let's see how we get the converted speech contain target user's voice characteristic. The user simulated speech is generated by adapting a deep learning-based voice conversion technique that transforms voice characteristic from one speaker to another. This generates new utterances in the target speaker's voice. Multiple simulated speech signals are generated and combined to form the my babble noise, which complicates recognition for the attacker because of the spectral overlap. We use convolutional variational autoencoder for the voice conversion system. A VAE-based voice conversion system is chosen because first, unlike conventional Gaussian mixture model-based approach, parallel speech data are not required. Second, this approach enables voice conversion purely from the audio data, where phonetic and lexical information about the speech are not needed. The training process is a reconstruction process. In the training step, the encoder takes the utterance from both a reference speaker and the target speaker, XN, and extract the speaker-independent information, ZN. The speaker identity vector SPK of the given utterance XN then concatenate with ZN and feed into the decoder. The decoder helps to reconstruct the audio with the same content of the given utterance XN and in the voice of speaker identity SPK. The result signal XN hat U should be the same as the input signal XN in the training process. In the inference step, by input the reference signal XN and change the speaker identity SPK to the target user U, the result utterance XN hat U will have the content of the reference utterance XN in the voice of target user U. The one-hot vector SPK is used to condition the decoder on the identity of the desired speaker so that the output audio XN can sound like spoken by target user U. The voice conversion is then accomplished. In the experiment step, we focus on attaining high word error rate against Google's state-of-art ASR system. First, for the victim user, we choose a male and female speaker from the IEEE dataset. Each speaker provides 720 utterances, and our goal is to mask out all the utterances by voice-converted utterances. Next, we choose a random speaker from Libya's speech dataset who produce 118 clean reference utterances. Then we use voice conversion technique to transfer the speaker identity of two target speaker from IEEE dataset to speech provided by the speaker from Libra's speech dataset. We produce different combinations of these converted utterances and stack different number of soundtracks together to generate the My Bible noise. First, we examine the performance of the ASR system on clean target speech as baseline. Both speakers achieve an 11% word error rate. We then determine how inject specific My Bible noise impact recognition performance. We test 6 different My Bible noise configurations. The My Bible noise is combined with different IEEE speech signals at 0 dB SNR. The number of generated utterances varies between 1, 8, 16, 32, 64, and 118 converted signals. The figure here shows the average word error rate of the different noise realization. For both IEEE male and female signals, the My Bible signal, the Bible noise that generate from 8 voice converted signals, which is the VC8, produce the highest word error rate. The word error rate gradually decreases as more converted speech signals are added. This is likely because as more soundtracks are added, each soundtrack creates too much overlap, and eventually the noise will be sounds like a generic Bible noise, which results in a poor defense. If too few soundtracks are added, such as only one soundtrack, VC1, there will be gaps revealing the target speech. For IEEE male signals, VC8 have 96 word error rate. This is much higher than the baseline Bible noise, which produce only 61 word error rate, and Kafi noise, which achieve a 60% word error rate. For IEEE female signals, VC8 outperforms all other noises with 92% word error rate. The generic Babel and Kafi noise perform similarly to the same IEEE male scenario with 59% and 60% word error rate. Besides ASR system recognition result, we also conduct a user study to evaluate how well the generated noise abstract speech against human attackers. We recruit 210 participants on Amazon mTurk, and each participant was presented with 20 audio clips. Each audio clips was mixed with a baseline generic Babel noise and our proposed 8 soundtrack voice conversion My Babel noise at different SNRs. The number on the x-axis indicates the mixed SNR level. Each participant was randomly assigned to one of the mixture conditions where they were asked to type the words they heard. The study shows similar trends as observed in the previous slides, where My Babel noise provides a stronger defense than baseline generic Babel noise. The VC8 My Babel mixture reached a word error rate of 81 at 0 dB SNR level, which much higher than the generic Babel noise. The water rate decreased to 97.7 if we lower the SN level to -5 dB. However, if we use SNR level higher than 0 dB, which indicates that the speech energy is higher than the noise energy, human listeners can easily recognize the speech. The mean at 5 dB SNR dropped to 37%. In conclusion, comparing to other defensive approaches, my babble noise mixed with speech at -5 dB SNR is a strong defense mechanism against human-based eavesdropping attacks. We also built physical MyBabble box prototype of our defense approach on the left, which is still far from the eventual vision on the right. This approach seeks to maintain the usability of the phone screen and speaker, yet allows for applications of the MyBabble defense on the microphone. As described more in the paper, we're also testing the disturbance level for injecting the noise. In the future, we may build a phone accessory similar to the right picture here, which can have embedded speaker in a phone case, which can produce MyBabble noise to protect people's privacy. For this paper, we evaluate obfuscating noise as a defense against microphone-based eavesdropping attacks. Through a comprehensive evaluation, we find that our personally crafted MyBabble defense performed best and help to mislead current ASR attacks as well as human-based attacks. Our proposed MyBabble noise mechanism uses voice conversion techniques to generate synthetic speech signals that can combine to form user-specific MyBabble noise. These synthetic signals have the same voice characteristic as target speaker, which further confuses ASR system. Future work should explore the application of generative adversarial networks, also known as GAN-based approaches, to automatically generated synthetic noise to fill the best possible ASR system. Also, our work focused on evaluating a single microphone scenario. Practical defenses uses MyBabble noise with multiple and directional microphone scenarios should also be examined in the future. Thank you for listening. We also want to thank NSF for funding this project. Thank you.